Good morning, everyone. I'm Jennifer Reeves, Senior Resident Fellow for Space Studies at the Mitchell Institute's Spacepower Advantage Center of Excellence. Welcome to this Mitchell Institute panel on one of the most critical technologies shaping the future of space operations, laser communications. As space becomes increasingly contested and congested, traditional radio frequency communications are hitting some limits. We're facing bandwidth constraints, security vulnerabilities, plus growing susceptibility to jamming and interference. Meanwhile, our adversaries are rapidly advancing their own space-based capabilities, making secure, high-speed data transfer more critical than ever. And this goes beyond space. The collaborative, real-time partnering attributes we'll need in the terrestrial domains will rely on connectivity, and laser comms will be a big part of that equation. It offers a crucial pathway forward, promising higher data throughput, lower latency, and inherent resistance to interception. But the technology also presents significant challenges, from atmospheric interference to the complexity of establishing precise links between fast-moving satellites. Success comes down to taking advantage of the positive opportunities while working around the technical challenges. So today we're joined by leaders from 3 organizations at the forefront of developing and operationalizing this technology. First, we're very excited to have Nathan Getz, Director for Data Communications at the Space Development Agency. Welcome, Nathan. Next, we are thrilled to have Trevor Haak, Director, Space Systems and Technologies for General Atomics, Electromagnetic Systems Division. Thanks, Trevor, for being here. And finally, we are grateful to be joined by Art Dhallin, Military and Strategic Communications, Mission Strategy and Advanced Capabilities, Lockheed Martin. Welcome, Art. So we don't have a lot of time. I'm going to jump right into the questions. So I touched a bit on this in my opening, but I'd love to just level set our audience. Art, we have basically relied on RF, radio frequency communications, to communicate with and between our space systems for over half a century. Same goes for our terrestrial capabilities. So talk to us about why this is likely no longer sufficient.
Well, first of all, a lot of people talk about laser comm and RF as an either or. We really need to think of it as an and situation. In that when you use your cell phone, you might talk RF, or your cell phone will talk RF to a cell tower. That cell tower then goes optical into the telecommunications network. The other thing is laser comm for a given bandwidth is just inherently more size, weight, power efficient. So what you're seeing now in all of our military systems, especially on the space side, is just a continued demand for an increase in bandwidth. RF can only go so far, so it just makes sense to go into a laser comm technology in order to enable that. The other thing people forget, the COTS industry has put billions of dollars of investment into laser comm technology. It's the backbone of all of our telecommunications. We're now finally at a point in time where that is being matured and space qualified, and we're seeing it demonstrated on orbit. So with the new CONOPS, with the maturation of the technology, it's now an option to be able to use within our systems, but you're always going to have both a mix of RF and laser comm together.
Okay, awesome. So let's hear more maybe from Trevor about the lasers themselves. So recently, GA successfully established laser communications between an aircraft and a satellite orbiting in low Earth orbit. It was a big deal. So can you explain more of the basics of laser communications and really the significance of this test?
Yeah, sure. So from a laser perspective, Art did a good job kind of teeing it up, so thank you, Art. Laser really, the simplistic form is it takes, and the beam is formed from a very narrow angle, creating that soda straw that we typically used to like to see and use. The challenge with that, though, is getting that soda straw aligned properly to have that successful link and maintain that link with the receiving antenna or system. And then how that differs from the RF, for that matter, it's very easy to get that energy on the receiving antenna, but it's very hard to get the phasing and the energy high enough to support the higher data rates, whereas it's just inherent from an optical comms and laser comm perspective. And then the other piece that I'll kind of mention that Art teed up as well is that because the laser comm and optical comms is based upon the terrestrial technologies, the technology is already there, like you said. It's already proven. It's not pressing the limits of power of electronics, how the RF systems do today. And then the last thing, as you mentioned, Boots, is that it's inherently LPI, LPD. Because of the narrow of that soda straw, and because of the phasing and the modulation, it's much harder to get in the signal path from a resiliency perspective.
Oh, that's great.
And then from some of the successes that we worked great with our mission partner in the Space Development Agency we took our decades of experience in using lasers, not just for optical comms, but also for high energy, for fiber, for super continuum. And we leveraged that and actually took the time to do the engineering and the build process validation verification using SDA standard, which is great. And we were able to prove out with the needed touch points from I would say two key aspects. One was what we call PAT, pointing acquisition and track. You have to be able to acquire, get that beam. Like I said, the hardest part is getting the beam on the receiving end from a terminal perspective. And once that's established from a link perspective, is now maintaining that link through the atmospherics, moving targets. I'll say we took the really big challenge here with this one from a moving target perspective. And you have an aircraft moving at one direction in speed, and you have a LEO satellite moving at sometimes the opposite direction and much greater speeds than what we're typically used to in prior demonstrations, whether it be from a GEO satellite. This, for the most part, stationary. And as a result of that, we were able to demonstrate our PAT processes and approach, validated those, and we also validated the ability to use the SDA standard 2.1.2 of 180 megabit per second link, error-free. And it was highly, I think it was a lot of firsts, and by the way, and probably more importantly, it was between two different terminals from two different vendors. And so I would consider that a first. And we look forward to doing continued tests with SDA using the 3.0.1 standard to get up to 2 gigabit per second. And we're already having those conversations today.
Oh, that's awesome. And we're going to talk about that more in just a minute. But
Okay.
First, I wanted to ask Nathan a question. That laser communications is critical for realizing the Pentagon's vision of long-range kill webs. By transferring data between sensors and shooters around the globe, right? It's very detailed. Command and control will also prove pivotal. So Nathan, how do laser communications enable new operational concepts that simply weren't available to us, possible even, with RF systems? I mean, what changes in military operations do you anticipate with this type of technology?
Yeah, thank you. And good morning. So I think that this test was a watershed moment. When you are able to communicate from a LEO satellite to a moving aircraft, I think opens up a lot of new use cases. With optical communications, you can simultaneously have high data rate and low observability. That's been something that's been long elusive, so we're very excited about that. A couple other things. We're heading into a world where for the first time we have lots of proliferated low Earth orbit satellites with sensors on them. So what that means is we're going to have an unprecedented amount of data coming down and available to us. So optical communications is it's very fortuitous. It's a linchpin for this new capability that we have and this new kind of world that we're heading into with constant sensors, hundreds, thousands of sensors up there constantly generating data. And we need ways of shuttling that data around, whether that's from between satellites or getting them from the space layer down to terrestrial targets. Another thing I'll say, as far as use cases go, is dynamic operations. So with optical communications, we need the ability to replan and be very flexible in our kill chains, in our kill webs. We need that capability, and with optical communications, we can now shuttle data around to different places and are better able to support dynamic operations. Another thing with making optical communications scaled up and ubiquitous is that when the marginal cost of moving data around goes to zero, we are now able to learn every node in a network, whether that's in space or on ground, can now learn from the other. So it's kind of like a compound learning effect. And so I'm speaking abstractly, but these translate into very real ConOps. And so we're very excited about all those changes that can take place in the way we operate.
I mean, that's great. And so I think the next natural question, though, is something that Trevor already hit on. And so let's go back and talk about sort of interoperability, right? Because that's what we're going to need to have for this vision of fast data and lots of it moving around very quickly. So one of our biggest challenges is ensuring that different vendor systems can actually talk to each other. We've seen some encouraging progress. York Space Systems and SpaceX successfully demonstrated an inter-vendor laser link test earlier this year. Of course, what happened with the GA test was fantastic, but it is no secret that the GAO has criticized SDA for not yet having demonstrated links between different OCT vendors as originally planned. So, how critical is this interoperability challenge, and what's being done to ensure that we don't end up with incompatible systems? And Nathan, let's start with you. This will be for everybody, but let's start with you.
Yeah, sure. So SDA did, years ago, SDA released an open optical standard that was, I think, a kind of a new thing to release it on the web, essentially, and have vendors be able to build to a single standard. That standard has now evolved. We have a number of different vendors. They've built optical terminals. As Trevor said, we've done many demonstrations now between different types of vendors and space to space, space to ground, space to air. So we've demonstrated that. That standard also is has been, I think, a sort of a bootloader for other optical capabilities that I'm now seeing out in the world. So, and we're constantly evaluating, like, where that needs to go. I would expect that initially you're going to have some challenges when you're trying to integrate lots of different vendors and their optical terminals. But we're working through those, and it's, I think, picking up speed, and we're gaining momentum and kind of getting a critical mass now. And as you know, we just started launching Tranche 1, so we're going to start to see that scale up as well, and connecting up those optical terminals in addition.
That's awesome. Well, and I think that GAO report, it missed something, my opinion, about the importance of an iterative sort of spiral design process and deployment process, which I think is actually happening. So, Trevor, as you answer this question, give me your thoughts on that as well.
No, absolutely. First off, I think, I don't think I know, SDA had spot on when they moved out. And I think in some ways got some unfair criticism early on. I think they were trying to push the state of the art with the optical comms terminals based upon what they knew at the time from a market perspective and where and how we supported it. Because General Atomics, we've been involved with optical comms for over a decade and been part of the I would say the community establishing those standards, not just the SDA standard, but also the other standards that even ones that SSC uses in other customers. And as a result of that, we kind of followed Secretary Mink's mantra of innovate, innovate, innovate. And so we put money down, both internally and as well as from customer funding, to actually develop a modular terminal that is supportive of any domain and any type of standard that they wanted to employ. The difference is usually in the back end and the modem side of the house. And so as a result of that, we've come up with a product line that supports the various different domains in which these terminals need to operate, including the ground. And so we use that expertise to first demonstrate the airborne terminal from the ground and actually use that exact same terminal to connect ground via SpaceLink as a risk reduction before we put the actual terminal on the aircraft. And I think that paid out immensely. In addition to that, we also were able to use SDA's test and validation environment that they deployed to verify the modem-to-modem connection using their standard. And so that kind of helps with the interoperability aspects of things. And quite frankly, it actually validated our own test and verification facilities and processes as well over the course of that. So I think as we move forward, and we'll get to the EST one later, because I think we're going to talk about the kind of EST and how that is very similar, but yet in some ways different than with SDA's approach. But there again, we've got the ability now, because of the standards definitions, and be able to successfully build and operate using those standards, I think is a huge win.
Cool. Art, thoughts?
So from a prime perspective, I'm actually very supportive of what SDA did. I think they did it right. There's an ICD. We've used multiple lasercom terminals. We've also demonstrated connectivity with SpaceX, with a Lockheed Bird. And the fact that we've gone out, tested the SDA interoperability test bed, we've done everything SDA has set up everything to be done to minimize that risk going to orbit. So the real challenge has been just how quickly can we get them up there. There have been some scaling issues. We've worked our way through that. The other thing that I think is forgotten is SDA has a requirement for reprogrammability in the modem, which if you want to go fast and try to do an iterative approach, that's the way commercial technology does it. Get it up there, try it, do a software update, try it again. I'm very supportive of this approach, so I echo Trevor in that I think some of the criticism wasn't quite fair. The technology has moved faster in the past 5 years than I ever thought it would. That's largely been due to the demand signal industry seen from SDA. We've leveraged COTS. We've taken very much a go-fast approach. It's your typical technology maturation. But it has been, from my perspective, a success.
That's awesome. Well, let's hear a little bit more about the EST. So let me tee that up for you, Trevor. The Enterprise Space Terminal Program is aimed at creating a standardized, enterprise-wide optical communications terminal. So I believe that GA is just one of 3 companies SSC awarded a Phase 2 contract for on this program. So Trevor, would you lay out for us why these optical terminals are so crucial to enabling future laser comms development as well?
Yeah, sure. Over the course of the journey that SDA has been on, because SDA has been laser focused, pun intended, by the way, on the LEO layer and making sure that the network that they were trying to establish from a transport perspective actually worked from a crosslink perspective. But that has limitations, right? From a data rate perspective as well as ranging. And so holistically from a Space Force perspective, SSC took a step back and say, okay, we need to support this type of communications at longer ranges and at higher data rates to be able to basically to fill out that mesh network and give options for alternative comm paths to get the data around, both from a holistic network as well as down to the ground. And so as a result of that, they realized that there needed to be some level of development required yet in order to get the technology matured to the point where it can be commercially available, for lack of better terms. And as a result of that, they embarked upon a, no kidding, design, development, and prototyping effort, of which we were fortunate enough to be selected to embark upon SSC to support that mission build-out, simply because we had the discriminators already because of our investments. We had TRL heritage and actually data to prove that. Not that it works with the SDA standard, but also with the standard that SSC uses currently today because of our prior experience with the broader community. And so as a result, you know, they're now to the point where because of the successes of the program and the execution that we're seeing on our end, they are now actually going out and spiraling that into different form factors, higher data rates, and different distances, different orbits. So it's a similar approach, but very complementary, I would say.
Super. Well, so actually, Nathan, I'm skipping around a little bit, but I really want to keep going on this thread. So the PWSA constellation is expected to cost nearly $35 billion through fiscal year 29, which is a massive investment in an architecture that is heavily reliant on laser comms technology. At the same time, we're seeing rapid advancement in commercial laser communications capabilities, as we're talking about. So how do you balance the need for military-specific requirements against leveraging the commercial innovations to maximize the value of each RDT&E as well as procurement dollar?
Yeah, thank you. So at SDA, we are very interested in working with commercial, I'll say that. Number two, we are also aware of how fast the optical world is moving. I think Art mentioned that as well. And we are taking all of that as input. And I would say we're at a little bit of a crossroads right now. We're evaluating lots of options as we plan the future. And these conversations are going on within SDA and within Department of War and Space Force. So stay tuned on that. As far as commercial goes and making sure that we're not at odds with commercial, in my view, we don't want to compete with commercial. That's not productive. We want to leverage commercial. And I think the right type of research, a good research dollar, is one that incentivizes commercial to upgrade their capabilities to match what is needed on the defense side without undermining their business case, their commercial business case. That to me is a good use of these procurement and research dollars.
Oh, that's awesome. Yeah, and I see head nods here. Our contractor friends agree with that. Let's put it all to good use.
Yeah, the one thing I would add, I think, to that, Boots, is that in all fair, you guys had it right, Nathan, and so did Derek. You know, relying on a single network, it creates a single point of failure. And so I think by building out and providing the diversification of networks, whether it be RF or laser comm or optical comms, creates that inherent diversity that's needed to support the warfighters today. So you don't have an hour and a half gap because of an outage to support their mission operations, because 90 minutes is usually, even 90 seconds, usually is critical in certain types of environments.
Yeah, I think that's a great thought. And actually, I have a question that I wanted to pose about that. Last year, SDA successfully tested connecting Norwegian F-35s and P-8s over Link 16 via satellite, right? So this is a different thing. So do you see the RF Link 16 relay network remaining important as we build out the kill chain? I mean, I think I know the answer to that. Do we see everything going to lasers, or do we truly see a combined world with multiple pathways and multiple technologies in the future?
Yeah, I think it's what Art said at the beginning. So it's not an or, it's an and. You know, so we're always going to have RF. We're merging into scaled up optical comms. You know, the satellite in the last 10 years has gone from, you know, an exquisite thing to coming off the production line. Link 16 is, I believe, the largest Department of War tactical network in existence, and you know, so it's very broadly used. So in terms of breadth and depth of reaching your forces, it's very much still relevant. It's also used by a lot of our allies. So in terms of so that community has a lot of inertia. That being said, I think it is also fair to talk about, well, what comes next? And, you know, do we sunset Link 16? And I think the answers to those are yes. You know, we can debate the time frame, but Link 16, while valuable, you know, someday will sunset, and those discussions are happening. So in the near term, with our Tranche 1, Tranche 2, we are definitely building out a Link 6, I'll call it a global Link 16 network, where we can connect Link 16 nets terrestrially with any point on the Earth. And that's going to be very valuable. But there will be new technologies that come and supplement it and then eventually replace. I don't think that optical will completely replace, you know, Link 16 or an RF tactical network. Like I said at the beginning, that they'll be both.
Okay, yeah, I think that's reasonable, certainly for the time being. So now let's look further out. So one thing we need to start considering as we begin operating further past GEO, right? We're talking about terrestrial, we've had a conversation about GEO, and certainly in LEO, but we've got to get into cislunar space, right? And there are inherent time delays just associated with the vast distances in space. So I'm interested from Art and Trevor, with the inherent advantages of laser communications, of optical comms, How do you see them being a scalable option to get after the problem of deep space operations?
So a lot of people forget we've already done this to the moon. You had LADI, you had LCD, it's already been demonstrated. When you have those distances, it's really a function of bandwidth. You can do RF, I mean, Viking was RF, but you just have this little itty bitty soda straw of data back. If we want to get anything back that modern sensors can do, we have to have more bandwidth. You're only going to get that through laser comm. Now you have to scale it up. You have to worry about things like pointing stability, but those are all manageable issues. The further out you are, the more difficult it becomes, but I have a lot of confidence that we will be able to get there. I don't think it's that far of a reach given where the technology has matured to recently.
That's awesome. Trevor, anything?
No, Art said it perfectly.
Okay, that's perfect. So let's talk about a challenge, and that is that with laser communications, certainly tons of advantages over RF, but one big disadvantage is their tendency to be distorted by environmental conditions. So what are the most persistent environmental challenges facing space-based laser communications, and how would you like to address those, or how are we addressing those? Art, do you want to start with you?
Reality is you're always going to have weather. That's the issue
Yes.
with laser comm, and we like to put military forces in places where there's a lot of rain sometimes. So you always have an RF piece of it. From a ground perspective, you're always going to have site diversity. You're just going to have more sites to get the data down. The other thing is function of power. You can always get more power down there. Our systems, as they improve, will be able to get more power. And then finally, a lot of the applications we're talking about, you're above the weather. It's air to space. And so from that perspective, that mitigates it as well. So it goes back to you're going to have both, but it's just fact of life from a weather perspective.
Getting around it. So, Trevor?
Yeah, Art does a great kind of preamble. The only thing I would add to that are a few things. One, there are different there are different bands in which you can have these lasers. In our experience with the lasers, we have multiple types of lasers to support whatever the mission needs are, to include accounting for the environmental aspects of things. Including, for other distances, to the point where we've got our systems currently today. I mean, in fact, the system we've designed for the SDA as well as EST can't operate out to cislunar ranges. Are you going to get the data rates? No, because it's a range thing and power. But Art teed it up to the point where you can address the atmospherics using aperture size and power. There's also adaptive optics. There's also the different phase matching that you can use to kind of deal with it as well. So there's other ways that you can deal with the atmosphere. And so I don't see that as really a big hurdle to be able to implement an optical comms network.
Okay, I think that's great. So I'm going to take the next question, actually, and broaden our scope a little bit, and let's talk about the critical role that ground stations play in the entire enterprise of anything, right, that we do in space. We have to have ground infrastructure. What will the infrastructure ground requirements look like for supporting large-scale laser communications enabled constellations? What will that look like for us? Are they substantially different than what we do now with RF satellites?
So I'll make the point, I think they will be substantially different in that they're going to be a lot smaller. You're not going to have massive antennas when you start trying to get big bandwidth down.
That's good news.
Yeah, it's good news. Right now, the costs per ground station, they are more expensive, but when you look at probably cost per bandwidth, it's about equivalent. As you scale up, I'm confident that that cost is going to drop significantly. And so you're going to deal with it. You're going to have more of them around just from a proliferation perspective with weather. But I think they'll, at the end of the day, probably be cheaper and smaller footprints.
Oh, that's awesome. Trevor, anything?
Yeah, no, absolutely. I would probably, take a different view of how Art presented that. I would liken it to, there really isn't much difference. The real difference is having that receiving antenna be able to support the optical communications end of it, because once you get that data out of it and demodulate it, it acts a lot like current RF infrastructure today. So you can use you can use the current infrastructure that's in place today. You might make more efficient use of it because of the network that you're doing in space, from space to space comms and links. You could potentially have different ground entry points holistically, whether it be ground entry points or even from a disadvantaged user, tactical user perspective. It depends on the mission requirements. And from a General Atomics perspective, we have terminals from ground as well as across the various different surface aspects to include supporting disadvantaged users, just to be able to support those type of implementations. And so, yes, it is different, but I would say it would be optimized for the mission that's required and to support the higher data rates that a lot of our users are trying to get to today. Because a lot of them want to use, from an analysis perspective, an intel perspective, they want that raw data. And the systems we're employing today are much more exquisite. They're generating a lot more data. So you have to balance how much onboard processing you do versus bringing it all to the ground. And optical comms enables that mission set from an analysis and intelligence perspective to be able to better utilize and execute their mission.
Absolutely. So Nathan, any thoughts from the government perspective on ground stations?
Yeah, absolutely. So SDA is building out an optical ground network. We will use that network for our own purposes to backhaul data. We call those ground entry points, so Getz. So we're building out a network of those. We also have a number of test sites, and we've used those in some recent demonstrations. Those, a little more informal, but we use them so that we can opportunistically connect with satellites. And then we're also working with the warfighter community to develop what we call tactical optical sites and those capabilities. So kind of 3 classes of optical terminals. We are, we're excited because we see optical comms at an inflection point, and we see it starting to scale up, and we'll start getting economies of scale. So I think both Art and Trevor are right in what they've said. We're excited about the scale that's coming, and we're trying to be very adaptive to that. I'll make one kind of comment not related to your question, but SDA is, I will say, an incredibly adaptive organization. We're constantly, looking at fundamental assumptions, and we will reinvent ourselves as necessary to adapt. And so, and I think we've shown some of that in the past. So, yes, we are excited about the scale that is occurring, and we will adapt.
Oh, that's awesome. Okay, so this is an interesting one because it was announced earlier this year that the Space Force is planning its first laser communications test on a GPS satellite. So this could enhance precision and efficiency for billions of users worldwide. So this is a question for Art. How are you approaching integrating laser communications with legacy RF-based satellite communications like GPS? And tell us more about this test.
So from our perspective, what it basically is we're taking an EST, putting it on a GPS bird. You're really swapping one comm subsystem for another, but it's the same functionality, and given where EST is, we actually see this as a very low-risk approach. You have to do some mitigation. You got to make sure you have your jitter analysis done. You got to make sure all your interfaces are fine. But it's not that big of an issue. And then given the capabilities that you get to go along with that, we see this as a huge enhancement for minimal risk. We're literally at the point of looking at different bolt patterns and just making sure it fits in, because you're just swapping antennas effectively, and you're going with something that's inherently a lower swap. So
nice.
It's good all the way around.
Okay, you mentioned something, and I want to ask a tiny little bit about it, and it's the sciencey part of it. You mentioned jitter, and I think this is the first time someone's mentioned jitter in this talk. Can one of you guys briefly talk about what jitter is and why we have to deal with it?
I'll try, and then he'll correct me. When you point a laser comm, your stability is your link budget is dependent upon the stability of how well you can actually point in a single spot, because it's a really pencil narrow beam. So the more the platform moves, the more error you get into the link budget. And so if you don't have a stable platform, it's difficult to comm.
Yeah, and this movement is called jitter, right?
Jitter.
Okay, great.
And right?
That's what we have to do our best to avoid at all possible, as much as we can, is avoiding jitter.
And it's a known issue. Any optics you have, jitter is just something you work your way through.
Absolutely, Art, spot on. The only thing I would add to that is, the good news is, a result of recent demonstration we did for SDA from the air to space link, we actually successfully demonstrated the ability to lose link, both planned and unplanned, and reestablish link in time-relevant manner within the standard that's required. So I think, like I said, it goes back to the demonstration that the SDA just recently performed successfully, and being able to actually prove out that, yes, this does work and it is viable.
That's awesome. I mean, it's really exciting. So let's see. One concern that has been expressed about scaling the use of optical laser links has been if the supply chain and industrial base can actually keep up. So Dr. Tournier, a year or so ago, noted that supply chain bottlenecks, along with cyber threats, are his two biggest worries for SDA. So we'll start with Nathan. How is SDA working with industry to overcome these bottlenecks? And do you all see the supply chain issue as having resolved itself over the last couple of years, or do we still need some more effort in that area? Nathan, let's start with your thoughts.
Yeah, thanks. So SDA, we work extremely closely with our vendors. So when you put out an open standard and you have a lot of vendors building to that standard, of course you set yourself up for the integration task that follows. And it does take time for the supply chain and the base to build up. I think incredible progress has been made, and the fact that we're launching Tranche 1 is a testament that we've worked through some of those challenges.
It's happening.
Not that, there's still a road ahead, but we will work through those things.
Yeah.
And I think the supply, the manufacturing and the engineering base and all the suppliers are doing a tremendous job in the face of pretty heavy challenges. So yeah, I think so.
Oh, that's awesome. Okay, so Trevor. Thoughts?
Yeah, so from a cyber and supply chain perspective, absolutely, we're required. We just have to as a way of fundamental doing business. If you guys haven't seen and made it down to the show floor yet, we've got this wonderful CCA sitting there. Trust me, there's a supply chain that needs to support the back end of that. In addition to what we're doing from an optical comms perspective, as well as there are other parts of our portfolio from a directed energy perspective, as well as satellites ranging all the way from little tiny picosats up to larger than Espa Grande class, to EO/IR RF sensors, to nuclear power and propulsion, even fission surface power reactors. So it's from a large company, and Lockheed does the same thing, is you have to have a robust supply chain and vet that supply chain in order to meet the various different requirements so you don't fall behind and create risk either from a cost, schedule, or performance perspective.
Yeah, that makes perfect sense. Art?
Yeah, and as a prime, the supply chain is critical. And so we have struggled recently. Technology has matured, but scaling it up has been the challenge. I think we're starting to overcome that. Given the volumes that we see, and now it's more than SDA, it's EST as well. Industry is starting to catch up, but it's been a journey. I will say the best thing that we can do, and it's something I think SDA did very well, is you mentioned $35 billion of COTS investment, right? If we hadn't leveraged the COTS, you can add a couple zeros to that number. So the more we can keep the requirements aligned with the COTS technology and just minimize the amount of military unique requirements, the better off everybody is, and that will also help with the scaling aspect.
That's great. So gentlemen, we're almost done with this really interesting panel. So if each of you were to take 30 seconds and leave one thing with our audience, what would that be? And Art, let's start with you.
I'd probably say at this point, LaserComm is here. It's mature, it's ready to go. We are actively deploying it. It's not going away. It will get better, but we've been talking about LaserComm for at least 10 years that I'm aware of. I think we're finally at that point now where you're going to see it deployed operationally, and it's really going to come into effect.
Awesome. Trevor?
Absolutely, Art, spot on. I would foot stomp everything Art just said, as well as, hey, it's here, it's coming, get ready. Now let's find out how we can actually implement this on the various different platforms and not just doing one-off tests, doing the intersatellite links. This is coming to airborne, this is coming to naval, this is coming to whatever domain that we need to operate from. Look forward to supporting it.
Wonderful. Nathan?
Yeah, so it is exciting to watch something scale up in real time. Over my career, I never thought we'd be here, but I think we're at the high rate of speed of development and optical coming into play. And kind of back to one of your first questions to me, is that opens up all kinds of things. And I see a world where we probably have an order of magnitude, maybe 2 orders of magnitude more things that satellites are going to be talking to and controlling in the next 5 to 10 years. And we have to build a world that's going to support, we have to build satellites and communication systems that are going to support that kind of future. And so it's pretty exciting to be at that point.
It is exciting. That's the word that just popped into my head. So ladies and gentlemen, we've unfortunately come to the end of this Mitchell Institute panel. Don't forget to come on by the Mitchell Institute's booth and pick up some thought-provoking and very timely reports. And now, please join me in thanking our incredible panelists, and from all of us from MI Space, have a great space-powered kind of day.